a few comments. Everyone should have, I have yours in my office, Kyle,
Yeah, the quiz.
the quiz. Everything's been graded. Everyone should have received their quiz back
Or the grade, not the quiz.
and the quiz.
Oh. Oh, attached on. Okay, sorry.
Right. With comments. So if you, everyone in Florida received your quiz back, graded?
Well, you all get.
Okay, so that's the first thing. Second is that in Florida, your projects, you will need to obtain a registration code. You'll have to ask for registration. There's a link underneath the data mine. In fact, I can bring it up. And then we'll talk about the projects in detail after we finish today's lecture and also on Wednesday.
No class Friday, right?
Let me begin the class, and I'll share the desktop so I can show where it's on the DataMind website. The project in Florida, there's going to be data from, you're going to have to request access, and it should be pretty straightforward. It's an automatic
Approve or deny.
email back. What?
Approve or deny.
Right.
Yeah. Not the student should know.
To get to get to the website, it's through the National Center for Atmospheric Research, and what you're going to end up doing is comparing precipitation records for weather stations in Florida versus those in Colorado. You're actually going to have to combine two different data sets, and then from just the weather data, the problem's going to be to classify a weather station as either in Florida or Colorado. And then for the Adams groups, the data is going to be coming from a website at the NIH, National Institutes of Health. And well, again, I'm going to go through all of this in more detail, and I'll send out, or I'll put up on the website, detailed description of what the two problems are. So just to get, but the reason I bring that up now is that for the Florida group, in order to access the data, you're going to have to actually register at the, I think it's RDA. It's a particular part of the website at NCAR. And there's a link on the DataMind website for that. So, any questions about the registration for the Florida group?
Okay. Good.
Okay, so with that, we began on Friday, and I'm going to pretty much repeat, as most of the group here was not here, and most of the group in Florida was not here.
Yeah. It's my fault. I'm sorry.
Well, it wasn't my fault here, then, but most of the students were also not here. So, even with all that, it pays to go over. So I want to start talking about the how everything's going to work, and then I'm going to talk more specifically about each of the two pieces for the different groups, or the three pieces for the different groups. So with that, I'm going to start the summary again, the session.
Weren't you gonna show them the link on the website?
Yeah, I'll start and I'll begin by showing the, let's see, share the desktop. So first I'm going to show under, where did I put that? Under homework, let me refresh because this has changed. Under homework, there's now project information. So for the Adams State University group, there's a link, and I'll talk about, as when we get to the projects, what you're going to look for at this link from the NIH at the GDS browser, which files you're going to look for. For the Embry-Riddle group, there's another link, and let's see if I can bring that up to see. I think that because so if you click on that, it brings you to this web page, and what you're going to probably want to do as soon as possible so that you can have access to the data is, right now I'm logged in as guest, and so what you're going to want to do up at the very top is register now. And basically, it's a simple registration form with your email, your password that you want to have, and then your user information. And if you have any difficulties with that, let me know, and I'll get the data sets to you some other way. But the easiest thing to do will be for the group at Embry-Riddle to begin this registration process so that we can go through and explain how to get the data sets after that. So, any questions? Let me, any questions on the registration process in Florida? Their mics off, but they should be hearing, so.
So we'll assume.
Use the little hand icon if you have a question. We're good?
It looks,
Oh, there's one.
Yes, one.
where did it go?
Turn on
Yes,
the
one.
microphone.
Okay. I registered on the
Oh, I registered on the site, okay.
C.
They
can hear you.
I thought they just wanted the Colorado or the Florida.
Well, there's going to be two
They want
sets, and I'm going to
Florida.
talk about which two sets.
The
because-
handout. The little handout.
Can we just turn on their mic?
Yeah, let's do that. You may freely speak with the microphone.
So that just means down here.
That means one high five.
Are you there?
I'm here? Yes.
Yeah, I was just wondering, you just want us to grab those two data sets, because they also have available, you know, the full national data set.
Right, you know which one I'm talking about? Because there's a whole bunch of sets. You're looking at the precipitation records, I think from 1980. I don't have my
Yeah,
past.
the one I'm looking at is precip records from 1970 to 2009.
Okay, I'm wondering if that's, I don't have my login information here, so I can't actually bring up the data sets I was looking at.
Well, let's go with that.
But we can go with that, and then it should have it by states, right?
Yes.
Every
yes, it
single
does.
state. And so the two that we're interested in for your group will be just the Florida and Colorado. What we're going to end up doing is merging those two data sets into a single data set to train and test on that set. Does that make some sense there?
Yeah, so basically we want Florida and Colorado in one ARC file so we can analyze it.
Well, we're gonna have to, I don't think it's in the R format.
Yeah, we are looking at it in Weka, right? So
You're right, we're gonna have to work, we're gonna have to label also each instance as coming from which of the two data sets is it coming from? Right?
Okay.
So, because those are gonna be the classes, so there's a number of factors that, and I'm gonna write all this up, and have this ready for class on Wednesday. But basically, one of the things you're gonna have to do, you're gonna have to merge those two data sets. You're going to have to add an extra column. And the way the data is formatted is going to make it actually fairly tricky. There's gonna be a lot of zeros because of the way the data is formatted. And I want to talk about that more explicitly when we get to that point. Right now, all I'm interested in is that everybody in Florida make sure that they have the registration information so they can grab the data sets. Does that make sense?
Okay. Yes, sir.
Okay. And we're going to have to talk through what is the format that the data is in, because it's not in the prettiest format. Everything's written originally with Fortran in mind, going back to 1970. And so the columns are what dictate where the information is. And that's always, I kind of mentioned this early in the class, that the data is almost never in the format you want it in. Does that make some sense there? So how are we going to get the data and make it look like what we want? That's going to be the hard part.
Right program.
Well, they actually have some tools on the in-car website that we can take a look at as well. Okay, so let's finish up with the summary, and unless there's other questions in Florida for now. Move on?
Yeah, move on.
Okay. So let's start back up where we were on Friday when things got messed up. And we're starting to put everything together. And what is this entire pipeline from raw data to the finish going to look like? So, as I said at the beginning of the class, probably the most time is spent getting data to look like what we want it to look like. That maybe not, because I mean, you're also going to have to play with the different algorithms. But first thing is going to be to gather and understand your data. Coming from various sources. What's the format? How is the data determined? And again, I'm repeating what I talked about on Friday for those who were here, but what are the possible errors in your data? On the screen, I list a number of possible places. With the Florida group, it's not that you have missing data, but that we're going to have to kind of transcribe the data into a format where our data mining algorithms can apply.
Never mind.
Yes, what was your question, James?
Well, like, so errors in the data would be like the format it's in, pretty much. Because how would you, like, we have like 100,000 data points, how are we going to know there's errors in that?
Well, you want to be aware of where possible errors will come from. You're going to look for possible outliers that make no sense. It's like sometimes there's a transcription error. If you're looking at 100,000 points, unless you want to go through manually and search for that, it's going to be difficult to actually determine the errors, but be aware that there probably are errors. Sensor equipment, human error in measurements, clerical errors, notice I mentioned transcription, 1-2 gets written as 2-1. So one of the things one of the things you might look at would be things that just make no sense compared to everything else, outliers. What are you going to do with that? Or probably a big one, and Florida's going to see this because of the formatting of the data, we're gonna have to put in probably by hand a lot of zeros.
So that's where errors become from.
So, and how are we going to do that? And so I'll talk about that when we go through the actual projects. Noise, I mean, there's all kinds of possibilities for error. We won't be able to catch all the errors, duplicates and so on. But you just want to be aware that your classification in the end is only going to be as good as the data that you get.
Okay.
This is more, what are you going to do? So this slide is, we're going to have to prepare the data. So first you have to gather the data, you're going to have to get it off the website for the two projects, the NIH website or the NCAR website. You have to look at the data, what's the format of the data, code it.
So if you were to like get your own data and not just like an actual data set that was already made for you,
Right?
do you just like, would you type that all in Excel, or how would you collect your own data?
Well, it depends upon the problem.
So if you're like looking at say like a currency exchange or something like
A
that.
what?
Like currency or stock market or something like
Stock
that.
market exchange.
Yeah.
For that, it's probably going to be less chance of error to use, not to type it in yourself, but to use Yahoo Finance. You can download
If you download the data,
all that information straight off Yahoo
and then you
Finance.
can use that and then just use your own stuff in the data mining.
Right, right. Now, there might be some, and there are sometimes some errors there that get introduced. I mean, just
Like-
as it's being transmitted, it can get errors or. But that would be the safest thing would be
Yeah.
to go, that data's already there.
Okay.
So as one of the first things you want to do is understand the form that the data is in. I mentioned the data for the Florida group. It took me a while. I had to look through this data yesterday carefully. You have a station ID at the start, but everything's scrunched together. But that has to do with the fact that everything was written using Fortran code. So columns, if you look at the documentation, there is documentation. The first three slots represented, I can't remember, but certain information. And then columns 4 through 11 gave some additional information. And then you had time and date. And that was all dictated by the column in the on each line, the column position. So, in other words, basically you have to figure out what format is this data in, and how can I use that? And how am I going to be able to translate this into the form that we want? And we will develop some tools to do that. I can easily do that for the data. And the way the projects are going to work is we're going to have data sets at various stages. So if you have difficulty getting from stage 1 to stage 2, I'll already have pre-built data at stage 2 so that we can move forward from there and so on. So there's no reason if you get stuck someplace, we get to restart and move on. So, what are your features? What do they look like? What is it that you're trying to determine? I've talked a lot about the Florida group. I'll talk more about the two Adams State groups data. You're basically gonna be using different algorithms to work through this, but it's the same goal, which is to determine the age given values for different gene expressions. So is it a youngster, is it an older individual? Okay? So determine the problem type, what does the data look like? So it's, in our cases, they're both gonna be classification problems. Here, I thought I moved forward. This is not moving. Oh. What sort of similarity measure should you use? So this goes to basically this whole subject, and I've kind of talked about it in terms of the projects a little bit already. In terms of what form is the raw data. We can look at that towards the end of class with the NIH data as well. And what form should your final data take? And that also depends upon the algorithm that you're going to choose for your classification. And we'll talk about algorithm choice in just a couple minutes here. And is that the same hand,
I
same
think so.
question?
I don't think that question's moved.
Okay. So, these are more general questions still, but how are you going to handle missing values? How are you going to handle your outliers? If you discover outliers, what are you going to do with them? Is that's going to impact, so you're saying you're going to just toss them, it's going to impact all the decisions made after that.
Well, I mean, if there's one outlier in one of the attributes, but that ends up being a useless attribute anyway, you're just throwing out valid data.
So you're going to look at where the outlier lies. Maybe that outlier is really telling you something, or maybe it's just a decimal error, which happens.
No one likes decimal.
How are you going to determine that? I mean, these are judgment decisions that you as a data miner have to make. So as you consider possible algorithms, you're going to ask yourself, okay, what forms does the data have to take in order to be put into the algorithm? Is it going to allow for continuous data? Does it have to be discretized in some manner, or even binarized into two bits? If you've chosen an algorithm, how are you going to have to transform the data into that form? In terms of the gene expression data for the Adams State group, a common technique there is to not look at the raw data, but to first transform it by taking the log base 2 of all the values before you actually start looking at the data. That's not going to be difficult, but that's going to be one of the steps that we want to try. And do you have so much data? I don't think in either of these cases we have so much data that we're going to need to be using sampling. But if you do, is that going to help speed up the algorithm? So you don't have to look at all the data, but you're going to just take random samples and run it through. If so, what sort of sampling? shortcut.
SVNs.
Okay, so here's a general, I mentioned that depending upon the problem type, there are sometimes specific algorithms that tend to work well for that type of problem. Text classifications as a text classification problem, typically linear support vector machines actually work quite well. Neural networks work quite well. Naive Bayes work well. Other choices include, for example, hidden Markov models. Moses can be applied there and had some good successes. If you're looking at trying to do optical character recognition, OCR, or handwriting recognition, neural networks tend to have really good performances, and the best performers tend to be even deep neural networks. Yeah.
So do all different types of these have like their own thing? So if like you were talking about like the optical character recognition and handwriting, most people would go to either neural networks and deep neural networks.
Or k-neural nearest neighbors.
So
Well, I mean, part of this is going to hinge upon also, and I don't know if that was on a prior slide that got missed, or, no, it's right here. It's gonna depend, this is kind of where I'm coming from. It depends on what does your raw data look like, what does your input data need to look like, right? So one thing that can come into play, if you have stuff that, wait, it's already in the format I want for this algorithm, so that's the simplicity argument, right? Apply it. You don't have to do any work, and maybe now you have kind of an out of the box, off the shelf answer right away. That doesn't mean it's going to work that well, but there's no harm in trying, right? But, right, I mean, the thing is, a lot of this comes from, at the bottom, experience. And that's why I gave that kind of shortcut for specific handwriting recognition. Over the years, neural networks have done quite well with that. But how did we discover that?
People tested it.
We just did a lot of different algorithms. We compared them against each other. There are researchers applying neural networks. There's researchers applying support vector machines, applying k-nearest neighbors, decision trees, Bayes nets, right? And they're always comparing, trying to get better results because they believe that they've made changes that will enable better results.
I just feel like there's so many different algorithms and so much detail into each algorithm. It's hard to understand every algorithm, what it does and what it's good for. Like I think
That's why I'm trying to give kind of some shortcuts here.
I think it'd almost be better to find an algorithm, research the algorithm, and find what would be good to use that algorithm for, instead of finding something and finding what.
Well, so here's this experience. What sorts of algorithms have worked best for you or for others for the type of problem at hand? And there are different types of problems. Text classification is different than say,
Correlation.
what?
Like correlation type stuff?
I think the next one on your list of things was genomic expressions.
Genomic expressions, I think I had some there which tend to work well, but decision trees work well. Here's where ensemble methods tend to work well. As I believe stacking works really well with a lot of genomic expression data. And where did we discover that? It's not all from first principles. It's like a scientific discipline, you're just applying different algorithms, seeing which one works better, and over the years you develop a feel for that. Although there are reasons people use certain algorithms, but vision recognition, especially lately, that's this optical character recognition, has come about through deep neural networks, tend to work really well. And basically, you know, the pendulum kind of swings. Neural networks go back to the 50s, and they've come in and out of favor. For a lot of things, a number of, just maybe 5 years ago, support vector machines were the hot topic because they were outperforming, even though they're really pretty simple to use, they were outperforming a lot of other techniques. And now some of the deep neural networks are proving to be better for certain types of problems. So, I mean, that's part of it, is the ground is kind of shifting underneath you, even as you try to get better
Did
results.
this support vector machine like come after like the neural network, and then they said it was better,
Right,
and then it's now just like shifting back, saying
that's exactly what I'm getting at there.
You just smart.
So perform a literature search, right? I mean, find out what has had really good success in the type of problem that you're looking at. Doesn't mean that that's going to be the best for the problem you're actually using it on. So once you've chosen an algorithm, there's still often a lot of work that needs to be done, as you should have experienced through the quiz. The parameter tuning. Okay, you can ask yourself what each parameter represents. Sometimes there's so many parameters you don't even have a clue what each one does. Who feels like that was the case? Cody? Nick? Sometimes you don't even know. What's a good setting? Right? So if you don't have a clue, how would you find out? Item 3, grid search. What does that mean? You're just going to try all kinds of values. Maybe you think the values should be between 0 and 2, but what value is going to be best?
You can't try every single value.
So you're going to go from 0 to 0.2 to 0.4 to 0.6 to 0.8, 1.0.
I think it kind of gets to that a little bit later when it says graph results as a function, and you kind of look.
So these are just ideas for how do you tune the parameters. So notice, if you're using Weka, set Weka to use the same algorithm with different parameter settings. Okay? If you're not using Weka, if you're using computer code, you could use a for loop. For parameter 1 equaling 0 to 2, iterate by 0.2. And that gives you, 11 values you're going to have to do. But if you have a whole bunch of parameters, you're going to be limited by it's going to be you can't necessarily do 11 choices for each of 10 parameters, because now you're looking at 11 to the 10th power. So you have to be careful. How many are you adjusting by, and how many of those parameters are you going to use? Because 11 to the 10th, it's going to take one heck of a long time. So that's not going to be necessarily feasible. This only works if you can limit the number of choices that you're going to look at, which gets to that graph results. Can you see any patterns there? Chances are no, but maybe it has some nice pattern, and you can kind of find. Tuning parameters is hard. I'm not going to deny it. And it can be time consuming. And it can be time consuming for the computer.
Tuning petameter?
If each run takes 30 minutes and you've got 11 to the 10th power, that's one heck of a lot of time.
You get back to me on how long that'll take.
You can figure it out. So visualization. Can we use visualization to spot any patterns? That's what that graphing comes down to. Does it allow us to estimate better parameters versus worse parameters? Chances are the parameter space is going to, the performance over parameter space is going to be nonlinear. Which means you can't see, oh, if I increase this parameter, I keep getting better performance. Well, at some point, you're going to increase, that's not going to hold. And probably only for the particular values of your other settings is that holding. So you can't always say increasing is going to help. What? Can we use clustering to visualize? So, I mean, I'm not saying, what I'm getting at is this is hard. If you haven't discovered it already, it takes a lot of the, this is where I said it's as much an art as it is a science. We're going to try to find good parameters, and that's not always easy. There are some other tricks. And I mentioned when we talk about genetic algorithms, you can use the genetic algorithms to find better parameter settings. The genetic algorithms typically aren't used as a classification technique, but they can be used to adjust parameters. And that's a common technique and can be useful. Probably won't be doing that here. But just be aware that because it can explore, if you recall, for those who were, wait, was that Wednesday of last week? We went over, or Monday of last week? They go over, they explore very nonlinear, very kind of more chaotic spaces. So, data mining, algorithm choice, parameter sets. We're going to be analyzing results from different algorithms. Are we using all the features? If we're not, maybe we can redo the problem by getting rid of features we're not using. Right? Do the results make sense? And, pardon? Doe? Like duh, right?
No, like DOE. Like a deer.
Oh.
Sorry.
So, and that comes down to,
You misspelled.
Very last line.
Doe to results.
oh,
What up, Doe?
Doe.
so, and maybe you're not an expert in the field that you're looking at,
I'm not Doe.
okay? So you might ask someone in the field, if you're looking at genomic data, you get your results and it's like, hey, does this make any sense to you, a biologist who's studying genomics or molecular biology? Does this make sense that this would be the result? If not, is it a problem with what we did? Is it a problem that it's like, well, maybe the biologist said, that's odd, maybe there's something deeper that we're not considering in the field. You know, I'm just saying, do the results make sense? And that answer is not always straightforward either. I mean, beer and diapers,
Yeah.
getting back to that example. Does that make sense? If you think about it, it might.
It does make sense.
It does make
I
If I had a
sense.
kid, I would-
But at first glance, it's like,
if I had a kid,
What
I
the
would use
heck?
Mark all the time.
There's a picture of a grocery store and there's a sign and it said like baby food, baby wipes, diapers, and then at the bottom was wine.
That makes more sense.
that looks like a repeat.
Those make more sense.
Or grapes.
So,
You can make your own. What's wrong?
okay. We were there.
Sharpie.
Oh no, there's does there appear to be overfitting? How do you determine that? How can you tell? Basically, that's going to be in your evaluation when you do your testing. Because if you're overfit the training data, there's a good chance that when you get to the testing data, it won't do as well. Because overfitting means you're fitting the training data, but it's not robust enough. It's so specific to your specific training data that as soon as you get out of that realm, it doesn't do as well. Are the results reasonably well distributed? And what do I mean there? So, this happened to me a couple years ago. Oh, I'm getting pretty good results. This seems to be working. And then I just dove down, not even that deep into what the actual predictions were. It was always predicting exactly the same thing. It classified everything as in one group. That group tended to match what was happening really well, or better than 50%, which was kind of the judgment call there. But that's not really telling you anything, right? And so it wasn't really a good predictor. It was just saying, well, always predict in the San Luis Valley, if you're predicting weather, predict sun
And cold.
and cold
And
and wind.
And those.
And chances are you're going to have a pretty good prediction, right? But not better. It's not as good as it should be. It's just that if you did that every single day, you're going to be probably 80% correct. Am I off base on that?
No.
So, sun, wind, cold in the San Luis Valley, you've got an 80% correct guess. We're getting nearing the end of the pipeline. Evaluation. Evaluate the performance. Another typo, I see this one.
Oh.
How do you measure performance?
Oh, you measure performance?
How are we going to determine your statistical significance of differences? How good are your results in training versus in testing? It's essentially common sense stuff.
Always do measure performance.
What sort of testing should you do to evaluate performance? Probably cross-validation, which is built in on your WECA side. The number of folds depends upon the number of instances. If you don't have many instances, you're probably going to reduce the number of folds. If you have a lot of instances, 10-fold is not a bad number to use, for example. But if you only have, 15 data points, you're not going to get much out of it, but 10 folds would not be appropriate. Also, also crucial, and probably we're near the end of this, and then we'll talk about projects in detail on Wednesday, but write up your results. Why do I say that? In detail. Because as you're writing things up, you begin to notice things missing, or things that you didn't do that maybe you should have, or, oh wait, how do I know that? Kinds of questions that come up. So the more precise and specific you get as you write up everything in detail, the more you discover flaws in your procedure. When you've done write-ups for any class, have you ever discovered that?
Yeah.
Algorithms considered and why, parameter settings you used, why, any visualizations that helped in your analysis.
Why?
How should everything best be presented? How did you evaluate? How did you compare? I mean, these are questions you want to ask yourself as you go through the whole process. So I think that kind of ends the pipeline. And I will go in detail on Wednesday through each of the projects, outlining exactly what we're going to want to do for the group and the individuals in Daytona Beach, and for the two groups and the WECA, where each of you are going to be doing something different with the WECA group, and then the Moses group has enough detail that we're going to have to work things out along the way. But I'll go through all of that on Wednesday. Questions here before we get to the projects on Wednesday? No, Nick?
No, we're good.
Good? Questions in Florida, Daytona Beach?